All right. Thank you. Hi, I'm Youyou. I'm trying to define a one-pass CPS translation for dependently typed languages, and this talk is a short report on my progress so far. So I'm doing this as a step toward dependent type preserving compilation. So a compiler is said to be type preserving if it translates a well-typed source program into a well-typed target program. And this property is particularly important when the source and target are both dependently typed, because preserving dependent types would mean preserving various program invariants such as positiveness of numbers and sortedness of lists. In the literature, we have some results about dependent type preserving CPS translation. And the latest work by Bowman et al. Shows how to translate the sigma type using naive CPS translation. And this work aims to extend Bowman et al.'s results to a one-pass translation. A one-pass CPS translation does not yield any administrative redexes, so the translated program runs faster and is easier to reason about. And I'm going to show you what kind of new challenge will arise in defining such a translation. Okay, so as a warm-up, let us quickly review the naive call-by-name CPS translation in the simply typed setting. So suppose we have a source term second of E, where E has a simple product type. The CPS translation of this term looks like this. So it takes in a continuation K and applies the CPS of E to a continuation that takes the second element of the received value V and resumes with continuation K. And it is easy to see that this translation is type preserving. In particular, the types of the continuations required by and passed to the second of V are exactly the same. Now we do the same translation with dependent types. So suppose the source term E has a dependent product type. In this case, the whole term has a type that depends on the first of E. The CPS translation is the same as before, but this time the result is not well typed. We see that the type of second of V depends on the first of V, whereas the type of the continuation K depends on the translation of first of E. These terms are syntactically different, but it turns out that there is a way to prove that they are in fact equivalent. The intuition is that if the source term E is a pure term, that is, if E has no control effects, then the continuation passed to the translation of E will receive the unique value. This unique value corresponds to the result of evaluating E, and it can be extracted by running the CPS of E with the identity continuation. And using this fact, we can show that first of V is equivalent to the translation of first of E. Now the question is, how can we formalize this intuition so that we can use it in the type preservation proof? The solution of Bowman et al. Is threefold. First, we make the answer type of the translation polymorphic. That is, we add a type abstraction in the top level translation. And this guarantees that we can always extract the value of a CPS term in a type-safe manner. And second, we define a new typing rule for the target language. This new typing rule applies to application of a CPS term to a continuation, and it allows us to type check the body E2 of the continuation with the knowledge that the received argument V is a specific value. And this gives us the first two equations here. And thirdly, we add a new equivalence rule to the target language. This rule says running a CPS term E with a continuation K is equivalent to first running E with the identity continuation and then passing the result to K. This property is sometimes called naturality, and it gives us the last equation here. So using these techniques, Ullman et al. Were able to prove type preservation for their CPS translation for sigma and pi types. Great. So my goal is to prove the same property for a 1+ CPS translation. As I said earlier, a 1+ translation does not yield any administrative redexes. And one way of defining such a translation is to use a column translation, which takes in a source term and a target continuation as arguments. It is called column because the separator is usually written as a column, but here I'm using bar to avoid confusion with the typing relation. So, as with the naive translation, 1+ translation is easy with simple types, but when we have dependent types, we need to, again, solve the type mismatch when typing the body of the continuation. So let's see if we can apply Ullman et al.'s techniques to solve this type mismatch. The first step is to make the answer type polymorphic. This works well. It allows us to extract the value of E. And the second step is to define a new typing rule. And then we realize that this typing rule is not useful in our context. The reason is that a 1+ translation does not yield applications of a CPS term to a continuation. So now the question is, how can we use the knowledge about the unique value received by continuations? My current proposal is to use something that I call a definition lambda. A definition lambda is a variation of lambda that has a definition representing what value will be passed to the function. Its typing rule uses the definition to derive the body and also concludes with a type that also refers to the definition. The idea behind this definition lambda is actually not new. There is work on ANF translation of dependent types, and they use similar typing for contexts. But interestingly, this definition lambda poses a new challenge in 1+ translation. So if we use a definition arrow type to define the top-level translation of types, then the translation of a source type A would refer to the source term E, which inhabits the source type A. This seems to suggest that we need to translate terms and types in parallel, and that would complicate the type preservation proof of the translation. So that's basically my results so far. I believe that it is possible to define a 1+ CPS translation for sigma type, and I hope to report some positive results in the near future. Thank you.
Thank you, Youyou. Do you have questions? Got a few minutes.
This would be very nice if you can make it work. I got a bit confused by what a definition lambda is. It looked a bit like a let binding to me.
Yes.
Is it different?
Function. Yes.
How is it different from a let?
So in CPS translation, you need to represent continuation using as a function, right? Instead of a let. In A and F translation, it's fine to use let.
Okay. Well, I look forward to seeing the final version of this.
Thank you.
Very, very pretty talk. Is there any way of using, like, it seems like you've got these sigma types and you actually know what the left-hand side of the value of the sigma is, right? The first component of the pair. So maybe you could make that manifest in the type instead. So you have a sigma type where you know you record in the type what the witness is. And then maybe that gives you more information. It'd be a bit like your let, like you've got this function type that records in the domain what the witness is.
That's an interesting idea. Yeah.
Or maybe you could use singleton types in the target language, and that could be used to define these definition lambdas. I think.
Yeah, that's also possible.
Yeah, thanks for the nice talk. And it seems that one naive approach to the problem is to use Bowman et al.'s CPS transformation and then to reduce the administrative redexes. If Bowman et al.'s target language type system has a subject reduction, yeah, I'm wondering it works or why it doesn't work. Then why? Yeah.
Yeah, it would probably work. So the target language of Bowman et al., they did not prove type soundness, but just a translation to some known calculus. But I think, so for simply typed languages, we have this one-pass translation, and I would like to know if it's also possible for dependent typed language.
So more direct correspondence to the.
Yeah.
Yeah. Thanks.
More questions? Otherwise, I think we're done right in time for coffee. Thank you again.
Thank you.